Let's practice an Anova. You just saw, hopefully, the video that explained doing an Anova and also following that up with a mean separation test. We're using the Tukey statistic in this exercise, and so let's practice a little bit and see if we can put all that into motion. This is the example that we went over previously, so let's try a new one. And okay, so this little experiment is a little bit different, where what we have are different ways of providing supplemental lighting to ficus trees to keep them from dropping leaves. Isn't that annoying when you have a ficus tree in your house and it's dropping leaves all the time? Well, that's a lack of light in many cases. It can be other things too, but in a lot of cases it's lack of light. So would a fluorescent bulb, an incandescent bulb, or a plant grow, a sort of a specialty bulb, be the best for keeping leaves on? Okay, which source is best, and which would be the good choice for the homeowner? And of course we have a control which has no supplemental lighting at all. So we'll quickly run through, and we will do first the Anova. And again, the input range is everything in a box with the labels. You have this clicked, you are grouped by columns. And then an output range, you can just go out to the right, and there's your answer. So let's take a look at this here. Again, the all-important p-value, blow that up a little bit, 1.2 times 10 to the minus 8th. Ooh. So that's I think 7 zeros and then a 0.12. So clearly the p-value is less than the 0.05 threshold that we always look for to declare significance. But again, that only tells us that one of these treatments is different from one other. Okay, it could be this one different from all of these. It could be these two in a group together, these two, and so forth. Okay, so we would have to go on and do the Tukey test. And very quickly, we need a couple of numbers from this, as you recall, to use in the Tukey test down here. And this number here, 26.7, that's the error mean square. It's at the intersection of the within groups row and the MS column. This number here, 26.7. So let's go over the Tukey test. And we still have the old data in here, and so we're going to go and put this 26.7 in here. We need to tell the number of treatments, so we'll go back to the Anova, and we had 4 treatments. It says 4 already. Okay. How many samples did we have? Let's go back and look. Looks like there's 5 in each of these. Okay, so we wanted to replace that with a 5. And so we come back, we have our yardstick, or our Tukey statistic, of 9.36 roughly. Okay. So let's come back, and here it is. I already put it on here for you, 9.36. And I've put the treatments and the means right here. And I think you can see how I got to these groupings, which I've categorized with lowercase letters. In other words, this one is in a group of its own at the top. This is in a group in the middle by itself. Give it a B. And then these two are in a group at the bottom together. Okay, they're not different from each other, but they are different from that one and that one as a group. How do I know that? I apply the Tukey statistic. Okay, so is this mean more than 9.36 units different from that one? Yeah, it is. So I know these are different. And obviously, since these are smaller than this one, then this is different from both of these. So this one's in a class by itself at the top, more than 9.36 units from any of the others. How about this one? Well, we know it's more than 9.36 units lower than that. Is it 9.36 higher than these two? Yeah, it's 17, 18, 19 units higher. So it's in a class by itself, in the middle. And again, 20 minus 18 is only about 2, and that doesn't cut the mustard here for the Tukey. So those are in a class by themselves. So we've gone through all the different permutations that we can, and we find these classifications, and we would conclude that these two are among the best.